So this paper was motivated exactly by thinking about long-term asset allocation and long-term investment. And so basically when you're starting to think about those issues, there's a couple of things that are immediate. Number one is it's got to be about conditional dynamics of the returns. It can't, if everything is IID, the long run isn't any different than just a simple sequence of short runs, so that's not a particularly interesting thing. The second thing is that it's incredibly difficult. It's very difficult, partly it's difficult actually analytically to get solutions, but empirically it's a tremendous challenge because we have to try to estimate conditional expected returns in maybe a high dimensional state space. So it's a very complicated exercise. And as a result, I think it's pretty fair to say that most researchers, or very often at least, researchers and practitioners alike kind of resort to tools that develop more for myopic situations. So for instance, just like a 1 month mean variance type problem is something we see again and again. Okay, so what we're going to think about in this paper is kind of flipping the perspective a little bit. We're going to say, well, this is all very difficult stuff, but one thing we could think about doing is looking at returns at different frequencies. So if you're a 1 month investor, that's your horizon, you're interested in 1 month returns. But maybe if you're 1 year or a 2 year investors, you really want to look at 2 year returns, for instance, right? And the idea why that might be interesting, and we're going to call those different frequencies. We're going to look at them jointly, not just one at a time. We're going to call them multi-horizon returns. So you say this MHR acronym is going to pop up. And the reason, testing on or thinking about those things in unconditional moments and multi-horizon returns are interesting is that they will reflect conditional dynamics. Okay, they will reflect the conditional dynamics. And an example that we've been used in the literature, and we're not just going to do that obviously, would be variance ratio. So at the market level, not at the variance ratio measures unit per time. And as you increase the horizon, variance ratios tend often to come down because of mean reversion. Okay, so indicating long-run investors might be willing to hold more equity. So here's what we're going to do in this paper. We're going to use multi-horizon returns to test asset pricing models, okay? And so what we're going to do is take a bunch of models, standard models, and we're going to frame them in terms of a stochastic discount factor because I know how to accumulate the stochastic discount factor over time. I just multiply them together. What we're going to think about is, in that setting, what does multi-horizon returns do for us? And it is going to be a conditional test of the model. I'm going to show you that very explicitly as a general point. We're not going to talk too much about this, but we're going to develop a way to estimate a particular GMM estimation technique where we use multi-horizon returns as input, and we're going to argue that this is informative. Okay, and just to give you a flavor of why it's informative, think about a model that has a small error, but it's a persistent error. And so now, as you make that error over 2 years, it can become a large error, and that's sort of what we're going to exploit at some level. So the application we're going to have is linear factor models. And we're going to this is our null, and we're going to talk about an alternative later on. The M is the SDF, and then A minus B are some coefficients. The A parameter is effectively matching the risk-free rate. The B can be a vector of coefficients, and F is some factor returns. Okay, so if you want to think about F as like the HML, SMB, and market factor of French, that would be an example of that. And so that's going to be the set of models we're going to think about. In that set of models, we know that B times F is supposed to be the unconditional MVE portfolio. Okay, so that's kind of the classic, this is the SDF version of that. We're going to find sort of pervasive misspecification in basically all the standard models that can lead to, in some cases, large long-run pricing errors. Okay, and so then in the second exercise, we're going to sort of think about an alternative. How could we fix it? And we're going to add these multi-horizon returns to actually say something about what type of conditional dynamics we're going to show up as AT and BT, and these coefficients need to be time varying, and I'll explain why exactly. And that's going to be sort of very interesting. It's going to give us some sense of some kind of puzzling features of the data. Okay. So let me just spend 2 slides exactly delineating what adding multi-horizon returns does for us. So number one, the law of one price, conditional law of one price. We all know that. Just in notation, T minus 1 comma T, I'm just highlighting here that we're going to think about the maturities or horizons. So here's the exercise I'm going to go through right now. Think about the second bullet here. Think about a candidate stochastic discount factor that prices a set of assets unconditionally. Okay? And R's here are gross returns. All right? So now I'm going to ask the following question, which is the final bullet. What do we gain by looking at, say, let's say there was monthly returns. Let's think about 2 month returns. Now, what does that buy us? Okay? And if you look below, that's how you would gross up, the discount factor. The m's are just multiplied together, and the returns are here gross returns. If you want to think about HML, I'm just going to take HML and add the risk-free gross risk-free rate. Okay, that would be my gross return. So that's how you would do. That should still be equal to 1 if this is the right model. So now I'm going to do something. The first on the left-hand side here is the same as before. It's a 2-year MR, 2 months, I should say, MR condition. I'm just going to do the usual thing where I say if the expectation of x times y is the expectation of x times the expectation of y plus the covariance. Okay? So that's what I have on the right-hand side of that equality. And so that's the expectation of the 1-month return, t minus 1 to t, times the expectation of the 1-month return again, but from t to t plus 1. If that model works by covariance stationarity, both of those things are equal to 1. Then I get a covariance term, which says, well, if I want everything here to be equal to 1, that covariance needs to be equal to 0 then. And the covariance is mt minus 1 to t, rt minus 1. So mr should not covary then with m to t plus 1 times r to t plus 1. And that just says you shouldn't be able to predict m times r. That's a very baseline. M times r should be an expectation always equal to 1. So you can't predict it, right? So that's just what we're going to check. We're going to check if the pricing error, if you will, is going to be predictable. Okay, so that's the same as in usual. That's what the second bullet here is saying. Okay, so it looks a lot like, if you remember Cochrane's textbook, when he's talking about an instrument in GMM, you said there's a ZT he puts in. That's the instrument that could tell us about conditional dynamics. It looks identical, except the instrument here is endogenous to the model, right? I didn't pick it out of a hat or come up with it having looked at the data. It is an over-identifying restriction that comes from the null hypothesis, which I'm free to impose, right? And we can see if it might not be informative, maybe it's just very noisy and not useful, but at least it's a model implication we can test, okay? So just one quick note, we're going to look at multiple horizons, right? We're going to look at horizons 1, 2, 3, 6, 12, and 24 months, as it were. What you get when you do these GMM type tests are you get overlapping observations, and that's not a great thing if you want to think about a spectral density matrix, these type of things. So what we're going to do is we're going to use this trick we're using here to write a 2-period one in terms of the 1 period plus the covariance term. Because the covariance, we can always think about predicting 1 period ahead pricing error. And so we go through this more in a paper, but it's a very nice thing because our moment conditions won't be, under a null, they will not be autocorrelated. And this is important for the size of the test, okay? And in fact, we also do a bootstrap version here to account for some nonlinearities that might be important. All right, so that's kind of a technical issue, but that's how we're going to implement this. So the data on the models are, and like I said, it's going to be linear factor models. The data, we're going to do a bunch of standard models, like the standard CAPM. We're going to add sort of a betting against beta type factor constructed from Ken French's data. We're going to do the FF3 and FF5 if I'm a French 3 and 5 factor models. We're going to actually, I forgot to add, I was also going to add momentum to one of them. We're going to think about the Kent Daniel and co-authors have a new version of the Farmer French factor models where they hedge out industry risks, and those have way higher Sharpe ratios. Okay, so these are sort of very fancy, very high Sharpe ratio models. We have volatility managed Farmer French 5 factor a la Moreira and Muir. We have the Stamba and Yuan model, 4 factors. 2 of them are new, capturing some mispricing. So it's a roster of models, okay? The sample is the usual sample, 63 to 2017. The test assets, let me just mention this. The test assets are the gross risk-free rate. The base horizon is monthly. The gross risk-free rate. Then it is excess returns to the factors of the model itself. Okay, so let me explain that. Let's say you have the market factor. You can try to explain the market at the 1-month horizon, but you can also try to explain it at the 2-month horizon or the 3-month. And so you accumulate up the gross return to the market for 3 months and subtract off the gross return to risk-free rate for 3 months. Okay, that's the excess return. Why do we use those as test assets? Well, we do that because now I know that trivially the alternative where AT and BT in the stochastic discount factor are time varying, that alternative can price that model conditionally, right? The factors can price themselves conditionally if I allow AT and BT. Okay, so if that's that, so that knows, I know that there exists a model with time varying AT and BT that prices the long horizon returns. Okay, so that's why we set it up like that. Oh, just to mention, I think I mentioned, but horizons are 1, 2, 3, 6, 12, and 24 months. So we're sort of trying to get at a reasonable set of months. Okay, so before we start here, I just want to show you some, they're a little small here in the screen, but I want to show you some summary stats of these factor models, which are going to sort of inform where we're going here. So The plot A, B, and C are autocorrelations cumulatively over months. The x-axis is from 1 to 24 months, and there's a bunch of lines here. So, but that's okay. I just wanted to give you a general sense. I wish this thing doesn't exactly work, but if you look in the top left, the blue line is the cumulative autocorrelation of the market from 1 to 24 months. It's basically hovering around 0, positive a little bit until about 18 months it starts going negative. Okay, that's the market, but it's hovering around 0. If you start looking at the other factors there, that's the Fama-French 5-factor model, they're way more positively autocorrelated, okay? So you start getting a lot of positive autocorrelation. The scale is the same on all the 3 A, B, and C plots, okay? If you go to the Daniel et al. Factors that are just industry and other risk-hedged Fama-French factors, the autocorrelation is way higher, meaning that you're getting a ton of dynamics here, and that's a warning sign. Like if you want to invest for a long time and there's a ton of dynamics, you got to pay attention. Not for all factors, but for some of them. This bottom there is betting against beta and this down by Jan, so it's about the same. The bottom right is variance ratios for the MVE, in-sample MVE, mean variance efficient combination of the factors. I just want to summarize the model. For the market, I know the following about a variance ratio. It goes up a tiny bit above 1 as it increases the horizon, then it starts falling at about 18 months to 2 years as the mean reversion kicks in. These other models, the market is basically hovering around that straight line at the bottom. The other models, for instance, the DMRS model gets a variance ratio at a 24-month horizon above 2, meaning that if you hold statically rebalance back to the MVE combination of those factors, if you want to do that for 2 years, you're going to take twice as much variance per unit of time as someone who's doing this. Okay, so that might be a problem, right? So here we got to pay attention. But so anyway, that's just some motivating plots. Let me show you, again, this is not a formal test. Let me show you what happens if you calibrate each model at the 1-month horizon where it prices itself, the factors price themselves, okay? And then you look at pricing errors of the factors at horizons 1 through 24 months. We don't go that far out in time because we want to have sort of 30 independent years here, or observations, I should say. And so let me, again, the scale is hard to see here. Let me explain this. So on top, I define a pricing error. It's the M times R minus RF, okay? It should be equal to 0. Right? The scale of that investment is $1 because it's a gross return. So if you look at the top left here, market plus BAB, we start at 0. There's no pricing error at the 1-month horizon, trivially. If you go to the 24-month horizon, which is the end, and you look at the red dotted dashed line here, that's the betting against beta factor constructed with Fama-French data. The pricing error is in the order of 20%. Okay, so let's annualize it to 10. If you're trying to explain a risk premium of 6-7% and the pricing error annualized is about 10%, that seems like it might maybe it's just noise, but you know maybe there's a problem here. Stambon-Jan go up to sort of 40% for some factors. Some factors are fine, okay? The market tends to be more fine than the other factors. Fama-French, there's a certain factor, investment, etc., seems to have a lot of these dynamics. DMRS, same thing. You get these really big for some factors, pricing errors, okay? So here's what we do, and I'm just going to show you the end result of our test. Okay, we're going to formally test this with this GMM approach, these bootstrapped standard errors, and we're going to do it in 2 ways. The red bars are for a bunch of different models, is p-values. We're going to estimate on the 1-month horizon, and then we test on the other horizons formally. Okay, so you can do that. The other one, the blue bars, are where we estimate the parameters, constant parameters of the model. On all horizons jointly, okay? And so just to see if it could it perhaps still price it. And the answer is on the left you see the market. The market is not rejected, okay? So the market sort of prices itself, where I'm referring to at other horizons. But basically all the other models are, by and large, they're rejected at the 5% level. So a couple of them that sort of sneak above, but they're all kind of rejected, okay? So statistically speaking, we reject these models when they're trying to account for themselves at other horizons. All right. Then we do something puzzling because statistically you might think that if I increase the complexity of my model, it makes more errors. But economically, I think you might expect the opposite, right? So if the Sharpe ratio of a model, the maximal Sharpe ratio of a model increases, you should be getting closer to the MVE portfolio, and that should be the right thing. So you would maybe think that as the max Sharpe ratio of the factors is on the left-hand side here, on the y-axis, as that increases, we get closer to the MVE portfolio, we should maybe have smaller pricing errors on average on the test assets, which are the factors themselves. And if you press me on pushing a line through these points, it looks like it's kind of going the other way. You know, the higher the Sharpe ratio is at the 1 month horizon, the higher the pricing errors are at the multi-period horizon. So at least, you know, from that perspective, that's somewhat puzzling. Just a brief slide on this. You know, this GMM test always makes some people uncomfortable. So one thing we're doing is we're just doing a GRS test as well, which isn't formally a test of long horizon moments, but I'm just asking, hey, you know, can I kind of use these instruments, which is, the instrument here is the Z, M times R, which that's a factor return going H periods back. I estimate the M, right? It's going H periods back. Can I use that to kind of manage the return to the original factors, okay? And so this is all in the paper, but I can run a standard GRS test. And so the outcome is we reject all the models in this case, except actually Farmer-French 5 volatility managed is not rejected, although if you ask it to price the original Farmer-French factors, it still is rejected, okay? How big is the rejection economically? So we're using the information ratios you get from those tests, and McKinley has this small sample adjustment to get sort of an unbiased information ratio, okay? So the information ratios that are left on the table are kind of on the order of 0.5 annually, okay? So it's sort of a reasonably big number that's left on the table. So then the question is, you know, what's going on at some level? So how are these models failing? The way we set up the test, there is a conditional model, which is the second line here, where AT and BT are time varying, okay? That exists such a model that prices the assets, okay? So we're going to use multi-horizon returns to help estimate these B's, and then the AT is going to be nailed using the conditional risk-free rate. So we're going to get that out there. If you apply the conditional law on price, you have this expression here that BT effectively has to be equal to the expected factor return divided by its variance. Risk-free rate is also there; it's not a big deal. Divided by its variance. Okay, so it was never the case that actually these models assume IID returns. They didn't do that, but they assume that expected return and variances line up exactly. Okay, they got to be proportional. And so the fact that we reject means that they don't line up. That's really what it means. So we're gonna now we're gonna look at, okay, what does this variation look like? And so what we do, and this is a hard problem if you have multi-factor models, we're gonna take a couple of shortcuts here to kind of just illustrate. We're gonna look at the MVE combination of any given factor model. So take the in-sample MVE combination and just look at that one. Okay, so every model is a one-factor model now. And then we're going to get an observed BT as sort of, we estimate the conditional variance using an EGARCH on that one model. So that's sort of reasonably accurate. And then we do the realized MVE return. So it's kind of a noisy signal of what BT should have been. And then we're just going to project it on an AR12 type thing. We're going to actually make it, I want to restrict some parameters here. So I'm just going to make the two first lags. I'm going to allow for some first and second order autocorrelation. And then I'm going to have the same coefficient on lag 3 to 12. I just want to reduce a little bit and get sort of some sort of, so that's of the returns or these realized BTs. We also add in the conditional variance as a potential explanatory variable. And then we take the conditional expectation of this thing. What we're going to do is we're not going to run a regression here. We're going to let those coefficients be estimated by long-run returns. Because we want to ask, what is the information in long-run returns? It could be some very short-run kind of IID dynamics that long-run returns are not so sensitive to. Okay. So the first thing that happens, if you do that, the red bars are now p-values again for the constant B case. And then the blue bars are the p-values for the time-varying B. And so the point here that you should take away from this is that, generally speaking here, we do not reject anymore with our new specification. So I'll show you what these look like in a second, but just to give you a sense, I can construct now, you know, the optimal timing of this MVE factor given my estimated BTs. And so I'm just doing this here. And I compare that to the Sharpe ratio of the MVE portfolio with the constant BTs, which is the blue versus the red, and then the information ratio, what's left on the table from R, okay? And so what you should observe, you should really look at the blue here, which is the information ratios of the rejected model, which is everything except for the CAP-M effectively, are in the order of 0.6 to 0.8. That's kind of how we can improve on this MVE portfolio, okay? So it's kind of consistent with the GRS test, and that's the economic magnitude we're going for. What does it look like? So instead of plotting the BTs, we decided to plot the prices of risk, you know, the conditional Sharpe ratio. Okay, so that's the BT times the standard deviation of the factor. That's all it is. but it kind of looks the same. It's just a little bit more interpretable. And what this plot is actually just the average. It's kind of the first principle component across all models, just a straight average price of risk across all models. We just want to get at the big picture here. And so the average price of risk here is like 0.7, 0.8 across all these models. Obviously, it varies. And the yellow bars are NBER recession indicators. And something you can kind of see here is that, it looks like the price of risk, the maximal Sharpe ratio, conditional Sharpe ratio of these models is kind of low in recessions, which seems awkward, okay? And not all recession, the 2000 recession seems like it was high, actually. That was, where these models would predict a very high one. And so it looks like maybe there is something going on here which we have to think about. Now, let me do it a little bit more formally. I regress this thing on a recession indicator on the conditional variance of the market portfolio, on the dividend price ratio, on the term spread, and on the cross-sectional spread in betas from the betting against beta portfolio. All I wanted to see is that is there some sort of relation between the conditional risk prices gotten from those models and some notion of cross-sectional variation in some characteristic. And so we chose beta. We could have done the value spread, done something else maybe. So what do you get? So the recessions are statistically significantly negatively related to the conditional Sharpe ratio as given by these long-run returns. And that doesn't really depend on the other variables here. That's a pretty robust fact. The cross-sectional heterogeneity, how much spread is there in beta, is actually positively related. That makes some sense if I had done the value. I kind of wish we had the value spread in here now. It makes some sense to think that maybe the price of risk is high when there's a lot of difference in the cross-section. The market variance, the conditional variance of the market is negatively related to the price of risk. So that's consistent with this Moreira and Muir type thinking that, what's going wrong here at some level is that in recessions maybe, these variances spike and expected returns just don't go one for one with the variance, okay? It is weakly positively related to the dividend price ratio. That is not particularly robust, actually, depending on the regressors. And by itself, for instance, it's insignificant. What is robust seems that it is positively related to the term spread, okay? So that seems to be, that's consistent with some of our models. The R squared is only 9.6% though. There's very little. There's a ton of variation that we're getting here. Maybe some of it is noise, it could be, but there's a very low R squared relative to the stuff we're used to seeing. So at least, this exercise indicates that there is some puzzling dynamics of the conditional risk price from these standard models. Okay, so that's basically our paper as it is. The literature, just to conclude, the literature typically thinks about one horizon at a time, and that's totally fine. And if you got that exactly right, there would be no value to looking at multiple horizons. But we're seeing that if you don't have it exactly right, looking at multiple horizons at the same time is a conditional test of the model. Okay? What I like about it too is that we just use the model. We're not adding additional assumptions. No auxiliary variables are introduced. And they are informative, okay? So we kind of reject state-of-the-art models with relatively high information ratios. They're only asking themselves to price themselves, so to speak. I would say, if I was to say something about the estimates of the conditional price of risk, they don't obviously look like what I would have thought it would look like from a classic risk model, okay? We have substantial variation. The risk prices went from sort of negative 25 Sharpe ratio to positive 2, so there's a ton of variation in the Sharpe ratio. It tends to be low in recessions and is low when market variance is high, which most models would obviously give you the opposite. It is positively related to the term spread, but that said, most of the variation is not accounted for.